Thank you for this invitation also for presenting today. I'm quite happy with the presentations that I see today because actually I'm more from the printed electronics side, so it is interesting to see such volume of work on this. So, but today I thought on bringing a more innovative aspect, perhaps scientific as well, on the type of materials as a route for 4D printing or 4D printed surfaces. So I will just make a brief introduction of who I am and where I am, and then what are the topic, which is Block-copolymer self-assembly, and then go through important applications and open challenges for us, and then conclude today's presentation. So basically, I'm a team leader at Eurecat, which is the technological center in Catalonia region, and we work as a multi-departmental, multidisciplinary model, and we work as a technological center. We want to provide technological services to companies, and we still have to keep our foot on the scientific research or more fundamental issues so that we can push up and mature technologies. So actually in my group, we work holistically all the printed devices concepts. We go from the printed device development itself to create this function that we want. So there we deal with novel materials, functional materials, what designs, what materials, and so on. We also work then on the detection methods. We also develop ad hoc detection methods, miniaturized lab on chip as well. Also the ad hoc electronics, because the sensor, it's the structure that senses, but how you acquire the data affects the response. So we have to develop that as well. And then we work on that is our key technology, core technology, which is the fabrication and development. We are from printed electronics, screen printing, inkjet printing, spray coating. The last time we brought here a work was about from 2D to 3D. Using spray coating, particularly mounted on a 6-axis robot. And we also do the pick and place deposition. Then we also have integration technologies like for fluidics or for textiles or for smart patches, etc., etc. Just a kind of an example that it's easy to see the whole process is, for example, this lab on chip device created for a recently ended European project, which is called optogenerapy, where you can see I would like to know if you see how can I put the laser pointer? Now I see it.
Yeah. Okay.
Yeah. Okay. So where we developed the full device as a passive device with energy harvesting, with LED radiation. We then make all the circuit, we develop it for printed electronics, we make the fabrication in high volume in a pilot line, and then we integrate it, in this case, with injection molding. So it's like an in-mold electronics device, and with a microfluidics cell chamber included. So here today, as I told you, I was going to focus more on the material side, because printed electronics is a symbiosis between design, fabrication technique, materials to create the function. So if you change one of these parameters, everything changes, and you have to go back to research. It's why it's still in a technology that is still gaining maturity, although there is every day more robustness in our devices. And for example, as I create, for example, printed sensors from conductive inks, for example, is if I choose kind of just a different shape, I will be able to acquire a different response. In this case, why 4D printing? It's when we have a material that it's kind of a smart ink that has the ability that after printing and after some stimuli to create a dynamic structure. So this, of course, it's very, it becomes much more connected to 3D printing. But from my perspective, it's also from surface materials. It's very interesting from the thin films perspective and thin film devices, from 2D printed, let's say, to create a 4D printed material. So basically, the 4D printing is that you have a material that it's printable, of course. Then you have to have stimuli to create that secondary property, let's say. You have to have some organization inside your material to create that interaction, new interaction on the intelligence of the material. And what is really important is that it should be modeled. It should be predictable. So this is kind of important. So when you design your static structure, you kind of design it already based on the material that you know that will respond in some manner, right? So basically, just to speak about materials for 4D printing, the most usually referred to and definitely the most known is shape memory polymers, where you have the typical time response that you have the 3D printed object, and these shape memory polymers are able to have a different structure to accommodate the polymer chains in a way that you have a different structure at the end. In this case of this publication is with time, which actually time was the fourth dimension that was usually related to the 4D printing initially. But actually, there are other two types of materials that are becoming really interesting. One is hydrogels, and in this case, it's more about cross-linking and temperature, and liquid crystals. So in hydrogels, there are in these reviews you can really find all types of examples of polymers used, but typically really known hydrogels are great for this. Agarose, Hema, and other many Block-copolymers as well. And then on the liquid crystal elastomers, usually use long chains with supramolecular interactions that create these stack assemblies that form liquid crystals and are quite famous technology on their own. But so today, what I would like to show you, it's actually Block-copolymers. So focusing on Block-copolymers on the thin films, on the 2D, let's say from the 2D printing perspective, as a smart thing for 4D printing. A Block-copolymer is, by definition, is two polymers covalently bonded by synthesis. So you have usually highly chemically contrasting polymers. So usually, for example, I will speak today only about linear polymers, which is more simple, but they can actually have star-like or being tri-block. In this case, it's a diblock and linear hydrophobic, hydrophilic chain length. When you print them, this is kind of a glassy polymer. So you print it's a disordered material, and then when you print it, so after a stimuli, which is in this case called self-assembly, it will have a controllable fourth dimension, which actually, due to a controllable fourth dimension, we will have a microphase segregation, because this chemical contrast will, if we give the conditions, the polymers will crystallize head-to-head fashion. And so they will create these domains segregating the hydrophobic with hydrophilic chains. What does this mean? That we actually create chemical nanopatterns, and actually we can have here kind of a metamaterials with very interesting optical properties. Most importantly, these Block-copolymers are really, so they can be modeled. This is a FEMS modeling, so finite element modeling, with one polymer actually with the Block-copolymers are ruled by Florey-Huygens theory, where you have a very important parameter, which is called chi, which is the Florey-Huygens parameter, which is basically talking about how miscible are both blocks. The less miscible, the better they will phase segregate, which is what we want, right? And then there is an important factor, which is the radius of gyration. This means how bulky is the chain, and then the L0. All this will end up in an L0, which is called the periodicity of the features created in these 2D printed films. So in this case, this is the same Block-copolymer modeled for different configurations of radius of gyration, and we will obtain different chemical patterns of polystyrene and PMMA on surface, so different chemical nanopatterns on surface. What does this bring us is that with these materials, we can have predictable morphologies by controlling annealing conditions in time, temperature, and thickness of the printed layers. So Block-copolymers, moreover, Block-copolymers they have a self-assembly, and they have what you can call a directed self-assembly, which is a bit like the case that I showed you before, which is already on a surface. So that is already has a guidance. It's not a bulk material. It was not the bulk. It was the surface already confining the polymer. But when we can even induce more confinement rules, and those you can input in modeling when you include topographies, which is quite interesting also for the 3D printing application. So when one of these, if we print these materials inside channels, for example, you can induce ordering, and you can also induce orientation of the features. And so this is also modeled and predictable and predicted in models. These are really interesting for example, density multiplication in etch masks, which is one of great applications of Block-copolymers. Also, there is direct printing and of, for example, spray coating, inkjet, screen printing. We've tried also everything. And so we can control orientation of features, dimension of features, chemical nanopatterns generated, because these Block-copolymers are actually very much chemically rich. There are a great variety, and they are commercially available. For example, on the case of the graphoepitaxis, so on the topography's case, we can really play with the orientation. We can play with the surface energies where we print them on, and these actually can induce completely different configurations with the same Block-copolymers. And so what here we induce is first the printing. After the printing side, what we have to do is to create the annealing conditions that will end up in the microphase segregation. We can grow them on pattern surfaces, or we can actually apply pattern surfaces on them to create actually complex layers, and it again is the same strategy. So we have a direct printed glassy polymer. In this case, we are inducing the topography by embossing, and the annealing conditions, in this case, is swelling, and in the end, we can obtain a multi-layered alternating orientation chemical patterns that we are exploiting it for antimicrobial applications that I will explain you after. Again, so we can define a stimulus, which is the annealing conditions, and then we will have a result of this smart ink that is generating spontaneously a chemical pattern on surface. So one of the, there is a big application for Block-copolymers as photonic crystals because their nanopatterns of common Block-copolymers are usually on the visual range of optical diffraction. So actually in this, this very interesting application, it is used a Block-copolymer in a stack inside a stretchable assembly of a printed system. And the idea here is that when we stretch it, we are actually changing the distance of the chemical patterns, and so we are inducing a different refraction index. And so actually they could do an optical strength sensor. So this is kind of physical color, right? This is just it is a photonic crystal, and just by printing on top of a stretchable substrate. As chemical templates, one of the things that we exploited was the fact that, as I told you, so the two blocks, they generate these nanopatterns on surface. So you have basically hydrophobic lines and hydrophilic lines. So this contrast of the surface energy, what we used to demonstrate is that when we evaporate metal on top to create, for example, for different applications, but we observed how the metal actually sits only on top of the hydrophobic patterns. In this case, the periodicity, so the distance between lines, it's 20 nanometers, so it's really small, and it's just printing, annealing, everything on room temperature. And in this case, we evaporated, but it also works with infiltration methods of metal nanoparticles. And they also are ending up in ultra-thin metal layers templating. Okay, in this case, for example, here is the application that we pursued for high chemical contrast etching masks made in a low-cost, large area way. Another important application that is the one that we were focusing more as compatible with our kind of printed systems for medical devices or in-mold electronics for medical devices is that this chemical contrast, it's also a very trapping, it's very good for absorbing biomolecules. There is from 2008 already an application, the first publication on this topic. So this group demonstrated how proteins were absorbing on the interfaces only between the hydrophilic and hydrophobic parts. Here is the Block-copolymer already annealed. Here is just the polystyrene part. Here is only the PMMA part, and here is the Block-copolymer, but with a different annealing, a different morphology of surface. So you can see that they basically like the biomolecules in the proteins like to assemble on top of the interfaces. Following this case and the case of the type of nanopatterns with topography that I showed you before, we just filed a patent in 2019 that we demonstrated that these are actually quite useful for antimicrobial surfaces for blood applications. Why? Because if you want an antimicrobial surface, you can have superhydrophobic surfaces, nothing sticks on, and that's it, that's fantastic. But the fact is that when you want to do medical devices, like for example, the ones that I showed you in the first slide, that is an implant, when it's in contact with blood, if it's too hydrophobic, our blood sees it as, of course, a foreign entity and wants to take it off from your body. So
Claudia, can I?
Sorry.
Sorry, yeah. Sorry to interrupt you, but you have 2 minutes left. So
okay, it's my last slide,
okay,
more or less.
Okay.
So thank you.
Sorry.
So basically, almost. I really got scared. Okay, so basically what we observed was that actually the Block-copolymers are useful to absorb proteins, and then with the topographies we generated with the imprint and printing, we were able to create an environment that bacteria or cells absorb on top, but they are not killed by. And so this is really what we are exploiting for surfaces of our printed medical devices. So we could create control growth of biofilms in this way without having blood problems, so coagulation problems. So there are open challenges for Block-copolymers. There is the ink formulation. There are a couple patents of Block-copolymers for example, 3D printing as well. For 2D printing, it's easy. For 3D printing, you need to have a bit more problems for cross-linking and how that will disrupt the self-assembly. Then there is the resolution required for confinement commensurability. That has to have to be with the topographies. We are actually creating topographies with lithographic patterns. But the idea would be really interesting to pursue with 3D direct printing. And then the stability of the structures, which is something that we really work on, because this is already directly about printed stability of printed layers, and this is our core business. And so basically, this is what I wanted to share today, that these materials as smart inks from a different perspective to create really challenging and high resolution chemical nanopatterns from a easy printed perspective. And they are really a route for 4D printing metamaterials. And so thank you. This is my email if you want to know more about our research and our center, or if you have any specific question you want to put in private.